Hello everyone, and welcome to part 1 of our videos on the ellipse. So we're going to start with the geometric definition of the ellipse and the names of its various parts. So an ellipse is the set of all points in the plane, the sum of whose distances from two fixed points is a constant. And those fixed points are called the foci of the ellipse. So we'll look at the names of everything else in a moment, but let's just take a look at this picture. So what this definition says here is that if we take a point P on this ellipse, the distance to this point F1 and F2, and sum those distances together, you will always get the same sum no matter where this point P is on the ellipse. Alright, so let's take a look at the rest of our terms. So the points of intersection of the ellipse with the line through the foci are called the vertices. So that's here, V1 and V2. The line segment connecting the vertices is the major axis. So that's the line from V1 to V2 is called the major axis. And the midpoint of the major axis is the center of the ellipse. So that's right here at C. The line segment that is perpendicular to the major axis at the center and with endpoints on the ellipse is the minor axis. So the minor axis is this line segment right here. Now, to be clear, the center and the foci are not on the ellipse, but they are part of what describes the ellipse. All right, so let's look here. We've got all of our labels here if you want to just write down this summary. And I guess I did not label these points M, so let's go ahead and do that. So we could call this M1 and this point M2. So by definition, the sum from the point, any point on the ellipse, to F1, that length, plus the sum of the length from P to F2 is equal to 2a, which is a constant for all points on the ellipse. Okay, so I do want to take a look at this real quick so that we can see why that would be. So this distance a here is the distance from the center out to V1. So this property of the ellipse, that these sum of distances is always the same, of course applies on the major axis as well. So if I just draw that portion, so the distance from the center out to the first vertex is A. Now we've also got these foci here and here. So it's a little bit odd because what the distances we're actually concerned with are the distances from the vertex to F1 plus the distance from the vertex to F2. But if you see, this distance is going to calculate a couple things twice, if you think about it in that way. So let's see if we can make this as clear as possible. So the distance from focus 1 to the vertex is just this little red line that I've drawn. Now the distance from F2 to here covers this whole portion, and it covers this distance again. But that distance from F1 to the vertex is the same as the distance over here on the left side from F2 to the leftmost vertex. So the total sum of all of those parts is going to be 2a. Right, the distance from here and the distance from here. Hopefully that's clear. Now, the derivation of the standard equation of the ellipse is pretty similar to what we did for the parabola, but the algebra is much, much longer, and we're going to omit it from this lesson, as it would take a lot more time to go through. Now, we are going to take a look at the equations of the ellipse, and we've got a nice table here of all of our equation forms, and as discussed with the parabola, it's fine to look at a table like this for reference or to sort of confirm your understanding, but it's not ideal to use it as a crutch for memorizing these properties. They're not very effective in that regard. So there are a few things that we do have to keep in mind with ellipses, though, that are on this table. First of all, we always express A as the largest value when we're talking about ellipses, and B as the smaller value in regards to our equations here. So we have x squared over a squared plus y squared over b squared equals 1, or x squared over b squared plus y squared over a squared equals 1. So a is always the largest term. And additionally, we can see through the derivation of the equation of the ellipse that their relationship between a, b, and c is this b squared equals a squared minus c squared. Now, this looks like the Pythagorean theorem quite a bit, but it's of course not the Pythagorean theorem. Just sort of coincidentally is very similar. But that is very important, and we're missing one of our pieces of information for the ellipse. That equation is going to be the key to how we get it. Now, one thing I want to point out about this equation, one helpful way to look at this is to think of the equation of a circle with radius 1. That would look roughly like this. And I find it helpful to imagine the equation of the ellipse takes these values, a and b, and stretches x or y respectively by that factor of a and b. I think that that's a really helpful way to look at this. So if you sort of start with the circle with radius 1, which of course has equation x squared plus y squared equals 1, well, you notice the ellipse here could have been written as x over a squared plus y over b squared equals 1. So you can think of the a and b values as stretching your x and y axes for your circle into this elongated shape we call the ellipse. And that view is also helpful for understanding why we know if it's a horizontal or vertical ellipse based on which value is larger. So we always write a as the larger term here. So if a is paired up with the x, that means we're stretching the x further. And on the other hand, if a is paired up with the y value, as in the vertical ellipse, we're stretching the y-axis further. And so we get something that's stretched more vertically than horizontally. Now, here we have a summary of the vertices, the foci, the endpoints of the minor axis, etc. But I think, once again, it's best to focus on the graphs and understand the constituent parts of the graphs. So here we have the horizontal graph to the right. The distance from the center, 0, 0, out to the first vertex is a. So that means the first vertex is at point A, 0. And if we go that same distance a backwards to the second vertex, well, of course, we're going to have x is negative a and y is 0. For our minor endpoints, we're going a distance of b, and that distance of b corresponds to the minor endpoint 0b now because we've gone up by b. And the second minor endpoint goes down by b, so that's going to be 0, negative b. Our foci always land on the major axis with the vertices. And here we have the distance for the foci. We always label as C. That's the distance out from the center to the foci. So if we go out a distance of C from the center, that puts us at C0 for the first foci, or first focus, I should say, and then the second focus over here, that's going to be at negative C0. Now, if we look at a vertical ellipse, so this is one where our larger term A was paired up with the Y value. Well, we get the same thing, except that since A is paired up with the Y, it's going to stretch the Y-axis portion of our graph further. So we get stretched vertically, and we get for our vertices A0, and then negative A0. And then when we go from the center out to the minor axis endpoints, we're going to add B, that's B0, and we're going to subtract B, that's negative B0. And similarly for the foci, on the major axis, we'll go from our center and we'll add C. So that's this distance here is C. And then we'll subtract C down to our second focus. So we want to take this look, this way of viewing the ellipse, and use that to answer as many questions as possible. So we'll go through some examples here. Find the standard form of the equation for the ellipse satisfying the given conditions. Graph the equation. So what I want to do every time with the ellipse, just like with the parabola, is draw so that I can determine my information geometrically. So my vertex here is at 5, 0, so 1, 2, 3, 4, 5. We'll plot a vertex here. And it gives me two foci at positive 3, 0 and negative 3, 0. So we'll call this one F1 and this one F2. Now, it doesn't give me any more information, but I don't need any more information because my center is going to be between my foci. So that tells me the center is 0, 0. And then I just need the appropriate distances from my center. So the distance from the center to one of my foci is going to be C equals 3. And the distance out to my first vertex, let me just go ahead and erase that center there. It'll be a little easier. So my distance out to my first vertex is 5. So that's A. And remember, we have the relationship that b squared equals a squared minus c squared. And that's perhaps the only thing you truly need to memorize from this table. The rest you hopefully can understand from the geometry of the graph. So now I can find my value for b. So b squared equals 25, that's 5 squared, minus 9, which is 3 squared. So b squared equals 16, and b equals 4. And we're talking about distances here, so of course b is going to be a positive number. Now, when I go to write out my equation, I have to think, where is my a paired with? And since my vertex is on the x-axis here, that means my a is paired with my x value. So this is x squared over a squared plus y squared over b squared equals 1. And that's going to give me x squared over 25, that's 5 squared, plus y squared over 9, which is of course 3 squared, equals 1. And I'm also supposed to graph the rest of the ellipse, so let's go ahead and do that. Since b is 4, that means we will get to our minor endpoints, I should say, by going a distance of 4 out from the center. And now I have everything I need to draw my graph. So we'll just make our little elliptical shape here. Oh, I need one more vertex here, which that's of course going to be at -5. Well, it's not a perfect picture, but I think it gets the idea across. All right. Let's go ahead and take a look at another example here. Find the standard form of the equation for the ellipse satisfying the given conditions. Graph the equation. So here we have two foci at 0 and plus or minus 3, and x-intercepts at plus or minus 5. So let's go ahead and graph that. So we'll put one focus here and the other here. And then we have x-intercepts at plus or minus 5. Well, if those are the intercepts of the graph with the x-axis, and since our y-axis is the major axis here, that means these are going to be the minor endpoints, because our foci always lie along the major axis. So what else does this tell us? This tells us that c equals 3. That's the distance from my center out to each focus. And b, the distance to my midpoints, is 5. And once again, b squared equals a squared minus c squared, right? So that's 25 equals a squared minus 9. So 34 equals a squared. In other words, a is the square root of 34, which is a little bit less than 6. Well, that tells us we can plot our vertices at just under 6 and just above -6. And finally, we can connect our graph all together here. Okay, so now which equation do we have? Well, in this case, since our equation is stretched along the y-axis, our a should be paired with the y. And that gives me x squared over b squared, which is 25, plus y squared over a squared, which is 34. All right, moving on. Here we're given an equation, and we want to find the vertices and the foci for each ellipse. So I'm going to start by noticing that this is really the same thing as x squared over 1. And so since my larger value goes with my y, my equation looks like x squared over b squared plus y squared over a squared equals 1. In other words, it's a vertical ellipse. And my values for b are 1 and a is 2. Now, in order to graph the foci, I'll need to know the value for c. And once again, b squared equals a squared minus c squared. So that's 1 equals 4 minus c squared. So if I add c squared to the other side and move the 1 over here, I get c squared equals 3. So c is the square root of 3. And now we can go ahead and plot this. So this is vertical, so my A is going to go out from my center at 0, 0. I'm going to go up a distance of 2. That'll be one vertex, and down 2. That'll be the other vertex. Since B is 1, on my minor axis, I'm going to go out 1 in each direction. And my foci, so my vertices so far are, that's going to be 0, 2, and 0, negative 2. Obviously, my M1 and M2 are going to be 1, 0 and negative 1, 0, but we're not asked for those explicitly, so I'm just not writing them down. And the square root of 3 is going to be like a little less than 2, more than 1. It's going to be somewhere around here. It doesn't have to be exact. So this we'll call the first focus, and it's 0 and the square root of 3. And our second focus down here, that's going to be 0, negative the square root of 3. And now we can go ahead and connect our graph together. Didn't quite give myself enough room, but that's okay. All right. Well, that's it for that example. How about we tackle another? Find the vertices and the foci for each ellipse. Graph the equation. So in this case, our equation is not in standard form. So we got to get it in standard form, and we're going to do that by getting rid of all of these constants in front of x squared and y squared, so that we just have x squared over something and y squared over something. But we can do that a little bit more directly, because we know the right-hand side should be 1. So we're just going to divide each side of the equation by 100. Well, that's going to give me x squared over 25 plus y squared over 4 equals 1. And since this is x squared, my a is my larger value, which is paired up with the x in this case, so this is x squared over a squared plus y squared over b squared equals 1. This is a horizontal ellipse. And my value for a is going to be 5, and b is going to be 2. And in order to find my foci, I will need to solve for c. So that's going to be 4 equals 25 minus c squared. And I'll move the c over here and the 4 over here, and I get c squared equals 21. Or in other words, c is the square root of 21. Well, let's go ahead and try to graph this equation. Since it's horizontal, my a is going to take me from my center out on the x-axis. So that's going to give me a vertex at 5, 0. That's one vertex. And then my other vertex is going to be negative 5, 0. And since b is 2, I'm going to go along my y-axis, a distance of 2. And now I'm going to plot my foci. And c is the square root of 21, so that's bigger than 4, but less than 5. So it's going to be somewhere in the middle of 4 and 5. Let's plot it right here. We'll call that focus 1. That's the square root of 21, 0. And over here we'll plot focus 2, which is negative the square root of 21, 0. And we'll just connect our outer pieces all together. And that's our ellipse, with vertices 5, 0 and negative 5, 0, and foci the square root of 21, 0, and negative the square root of 21, 0. All right, and now we're given a graph, and we're going to try to find an equation for the ellipse that matches this graph. So here we have a focus at 0, 2. That's this point here. And it's clear that we're centered at 0, 0. So that means my distance c here is 2. And since this is going to be the minor axis, that tells me that b equals 3. That's the distance from 0 to negative 3. And I need a, so b squared equals a squared minus c squared. So 9 equals a squared minus 4 in this case, which gives me 5 equals a squared, or a equals the square root of 5. And this is a vertical ellipse, so our equation should look like x squared over b squared plus y squared over a squared equals 1. So that's x squared over 9 plus y squared over 5. I made an arithmetic mistake. That makes sense. Let's try that again. Somehow I got that 9 plus 4 is equal to 5. But this should be 9 plus 4 is equal to 13. And of course then a is the square root of 13, which makes much more sense because a should be bigger than b, right? This thing is vertical. So this should be x squared over 9 plus y squared over 13 equals 1. All right, well, that's it for part 1 of our videos on the ellipse. Thank you for watching.